Hi, Lauren. Yes, welcome back. I'm going to do example of the LCM here now. I might put this in as a different video actually, because yeah, so you can more easily pick up on this part, I suppose. So I'm going to carry on now with the same worksheet. We're going to do the LCM, but we're going to find it using prime factorization the same as previously. All right, it's very, very, very similar to what we just did for the GCF, just you're going to do a few different things at the end. This is still Math 1101A Unit 3 worksheet. So still worksheet 1. All right, so I'm going to do question 4. Determine the LCM. Actually, let me turn on the small example up here in the corner. I can zoom in quite a bit on this one. Determine the LCM of each set of numbers. Cool. Yeah. There we go. It's a good size. It's readable. So let's do B and then either E or F. Let's do B here. So 21 and 45. So 21, I'm going to start breaking this guy down. 21 can't be divided by 2 because it's an odd number. So once we get to an odd number when we're doing prime factor decomposition, then we have to start trying to divide it by odd numbers. Right? The most common odd primes we're going to be dividing by is going to be 3 first, then, 5. 5 is different, right? Because 5, we know if something can be divided by 5 by looking at the last digit of it. But we'll have to try 3s, we'll have to try 7s, we have to try 11s, sometimes we'll have to try 13s, even 17, 19. I mean, there's literally an infinite number of prime numbers. But in our courses, it's going to be heavily skewed toward the small ones. So we'll try dividing by 3 first. And look at that, 3 does work here. 21 is 3 times 7. Of course, that one's in our times table, so we know that. Right? We know that 21 equals 3 times 7. Easy. Now we're going to go on to 45. 45 again is in our times table, so I probably don't need to belabor this point. But we know that 45 can be divided by 5 because it ends in a 5. So it's going to be 5 times 9. And again, of course, from our times table, we know that 9 is equal to 3 times 3. So 45 is equal to 3 squared times 5. Not super difficult prime factor decomposition there, is it? Now, the lowest common multiple is a bit different, right? If we were to find the GCF here of these guys, the GCF would just be whatever was in common, right? So there's a 3 here, there's a 3 here, and so our greatest common factor of these two guys would just be the number 3. Right? But now we're trying to find the lowest common multiple. Now we know a multiple is always going to be bigger, right? But we want the smallest number that is a multiple of both these guys. So what we have to do is we have to, for each number, okay, I'll write this out in words actually so you have it here on your sheet as well when I send you these notes. And it is often the case with math. Sometimes writing out the instructions in words is a little less intuitive than actually working through it. But in words, what we're doing is to find the LCM, we're taking the largest quantity of each prime factor, and then we're multiplying. Well, what does that mean, the largest quantity of each prime factor? Well, here, right, the prime factors that we have in total, we have 3s, we have 7s, and we have 5s. Right? So what's the largest quantity of 3s that we have here? Well, there's 1 3 over here, and there's 2 3s over here. Right? So our largest quantity of 3s is this one. There's 2 of them. Right? What's the largest quantity of 5s we have? Well, just 1. And you don't have to do them in ascending order. That's just how I'm doing it. And the largest quantity of 7s we have is 1. The reason the order doesn't matter is because it's multiplication, and multiplication is commutative. It's a fancy way of saying the order doesn't matter. Either way, what we've got is 3 squared times 5 times 7, right? 9 times 5 is 45. 45 times 7 is, what, 90 times 3.5? 270 plus 45, 315? Yes, haha. Turns out I can still do arithmetic in my head occasionally. So the LCM in this case is going to be 315. So what does that give us? Well, 315 is the smallest number that is divisible by both 45 and 21. Right? 315 divided by 21 is going to give us 15. 315 divided by 45 is going to give us 7. So there we have it. Right? A little bit unintuitive how it seems at first, but in the end, we do actually get the LCM of these two numbers from doing this. Just one quick second. Okay. This setup is considerably harder to make videos in than the setup I had last year, because the setup I had last year, once I was making videos, that was the only thing I was doing, so there was no like getting distracted from the video by a half dozen other things all happening at the same time. Whereas this year's setup is much more, it's a very split focus. Let's put it that way. Right? Makes me feel like I'm working in a kitchen again. Attention being pulled in 30 directions at the same time. Anyway, don't worry about that. That's part of the job. I'm not bemoaning it. It's just the nature of the beast. Anyway, I'm going to carry on here. So let's do the LCM now let's do for E. The color is not coming through super clear, is it? I'm going to have to work on the color balance on my dock cam as well by the looks of it. It's a little bit, the green looks a little bit similar to the black here. Yeah, I'll just get this out of there. So, first up we have the number 20. Number 20 is of course 2 times 10, and 10 is of course 2 times 5. So 20 equals 2 squared times 5. You might have been able to get that from the start, of course, because we know 20 is 4 times 5. Next number is 36. It's unfortunate that so many of these are ones that we've seen already, but I'll just call it 6 times 6, 2 times 3, 2 times 3. So 36 equals 2 squared times 3 squared. Now we have 38. 2 times 19. Gross. 2 times 19. Yuck. Ah. Bleh. No, but that's right, though. It's right. It's, you know, I'm exaggerating. It's a totally valid answer. 38 is equal to 2 times 19. The reason I was saying yuck, gross, bleh is because of what we're going to see when we get down to finding the LCM. Because remember now, for the LCM, we need the greatest number of each prime factor, right? Now, there are, of course, an infinite number of other primes that we're not dealing with, but there's 0 of those, so that number to the power of 0 is 1, conveniently, which means it still does work out. So, yeah, I mean, I love how math is sort of buttressed already against pedantry. Anyway, this is the kind of stuff that's simply just for my own amusement that I mentioned it. So, what's the greatest number of 2's that we have? Well, there's 2 2's here, 2 2's here, 1 2 here. Right? So we're finding the largest number of each of the factors, like we say over here, to find the LCM, take the largest quantity of each prime factor, then multiply. So the largest number of 2's that we have is 2. So the largest number of 3's that we have. There's no 3's here, 2 3's here, no 3's here. So we have 3 squared. What's the largest number of 5's that we have? 1 5 here, 0 here, 0 here. 1 5 is the largest. What's the largest number of 7's that we have? Well, there's 0 7's here, 0 here, and 0 here, so we have 0. That's what I was just saying, right? We could put in 7 to the power of 0, but any number, right? This is worth jotting down maybe as an aside. Any number to the power of 0 equals 1. That's just a little note off to the side. But any number at all to the power of 0 is always 1. So that's why, there's 0 7's here. So we are multiplying by 7 to the 0. Because multiplying by 1. Multiplying by 1 doesn't do anything. Right? There's no 7's. There's no 11's. There's no 13's. There's no 17's. But there is a 19. Right? So we do have to put in our times 19 over here as well. Right? So if we were just finding the LCM, for example, of 20 and 36, we wouldn't need this 19. But because 38 is in the mix, messing everything up, right? Anyway, it's just going to make our answer a little bit larger, that's all. It's still totally the same. Okay, so we have 2 to the power of 2, right? Or 4 times 3 to the power of 2. Oh, my goodness. TI-84. TI-84, what are you doing to me? So 2 squared times 3 squared times 5 times 19. Not going to do that one in my head. That one is going to be 3,420. So a rather large number for the lowest common multiple of 3 two-digit numbers. But, it's the way she goes. So that gets us to the end of the material for worksheet 1, I think, or the end of the examples that I'll do for worksheet 1. I hope that's a little bit clearer there now. I am going to carry on, like I said, now that I'm here shooting this and have everything set up. I'm going to carry on and do some stuff on worksheet 2 as well. Let me zoom out a touch. As these are, like I said, these are all related topics. They are not exactly the same by any means, but they are definitely related. So I'm going to do a little bit of these, expanding and simplifying as well. Ugh. I might have like hours of video shot for you to subject yourself to. Hope you got some popcorn. These are not. I don't know. I don't like saying, oh, these are not difficult, because obviously if people find them difficult, it's just because you don't really understand how to do them yet, and that's totally fine. That's part of math, is learning how to do stuff. It doesn't necessarily help for the teacher to say, oh, well, this is easy stuff. I'm not saying that it's something that you should already know, because there's no way to know it only learning it. But once you get how these work, I think you'll see, oh, yes, I get it now. It's nothing huge. All right, so this is going to be Math 1101A still. This is worksheet 2 now. Oh, right, unit 3. Who cares? It's Math 1101A, unit 3, worksheet 2. Whatever. Okay, so I'll start off with 1A. It's going to be 2x outside of 5x minus 7. Right? So what we're dealing with here is binomial multiplication. So a binomial, well, all that is sort of a number expression that has multiple different terms in it. Now, what's a term? A term in math is anything that's separated by a plus or a minus. Right? So this is something that I explained previously in the emails that I sent. But like I said, when you're explaining math just in a paragraph of text, it doesn't always make a ton of sense compared to actually seeing it here like this or hearing it talked through. I'll copy down some of these notes. Let me remove that window so you can see it. A term is part of an expression separated by part of an expression separated by plus or minus. We multiply binomials, we multiply each term. I think that's enough. That's enough written explanation there. And I'll show you what it means. Okay? So what it means, outside we have one term. So let me just... This is a term. Right? This is a term. And this is a term. Right? So now when we multiply, what we're multiplying is 2x by 5x minus 7. So this term outside gets multiplied by this one on the inside, and it gets multiplied by this one on the inside, like so. Right? So what we end up with is 2x times 5x minus 7. Oh, sorry, I'll do it in the same order. Minus 2x times 7. Now, this is sort of an intermediary step. We don't always see this one written out, but that's what's happening. I'm taking this 2x and multiplying it by this 5x. I'm taking this 2x and multiplying it by this 7. And the operation in between them is going to stay the same, right? It was a minus here. It's going to be a minus here. So we're going to end up with 10x squared minus 14x. Now, why is that? Well, when we multiply these together, right, first we multiply our coefficients, the numbers. 2 times 5 is, of course, 10. Then we multiply our variables. So we have x times x. 2x's multiplied together is x squared. Right? Just like on our previous pages, right? If we go back to over here, when we had 5 2's, we put them together, we call that 2 to the power of 5. Same deal for x's. When we have two x's together, we call those x to the power of 2. And that's minus 14x. And that's all you had to do in question 1. Like I said in the email, it says expand and simplify. We're actually not really simplifying, we're just expanding. If we scroll down to one that looks perhaps a little bit more difficult here, let's say I was to just really go all in here and start in on E. Let's do. Actually, no. Let's just go. Let's go right to the. No, I'll do E. I was gonna say let's go right to the top and do F, but F and E are basically the same. So it's 5a to the power of 4 b outside of 3a cubed b squared minus ab squared plus 6b. Holy cow, that is a lot of letters and numbers and crap all thrown in there together, right? But it's actually exactly the same as what we just saw. This on the outside is one term, right? So this is a term, this is a term, this is a term, and this is a term. Okay, so this term outside gets multiplied by this one, it gets multiplied by this one, and it gets multiplied by this one. I might have written it a little bit too close to the previous example. But anyway, hopefully it's easy to see which one goes along with which. So this next step is going to look rather large, but this is sort of the intermediary. What we're doing is we're taking this term outside and multiplying it by each of the ones inside. So I'm going to call this 5a4b times 3a cubed b squared. Now minus, because remember, just like up here, we keep the operation the same in between them. So I'm going to call this minus, and that's going to be 5a to the 4b times ab squared, and then plus, because again we keep the operation the same, 5a to the 4b times 6b. Right? Don't let the length of it intimidate you or anything like that. It's exactly the same math, exactly the same workings as what we saw up here, just now there's a bit more of it to write down, that's all. It's more in the wrist than it is in the noodle. Anyway, what we're doing for this next part now is the same as up here. First we multiply our coefficients. 5 times 3 is 15. Then we multiply our like terms, right? So a's multiplied by a's, b's multiplied by b's. And we know when we have a to the 4 times a to the 3, if you'll remember back to your algebra prep courses that we did, when you are multiplying numbers with like bases, you add the exponents. So this is now going to be a to the 7, because 4a's here and 3a's here. There's 1b here and 2b's here, so that's going to be b to the power of 3. Right? Now subtract. This next one has a 5 and a 1, so that's going to stay being a 5. A to the 4 and a to the 1, or just a, is going to be a to the 5. And then b and b squared is going to be b cubed again. Now lastly, for the final step, we're going to have plus 5 times 6 is 30. A to the 4 is just a to the 4 still, because there's no other a. And b times b is b squared. So there we go. That is how you're going to go about doing question 1 on worksheet 2. So you just, and at this point we're done. Right, so all we were doing is taking this term outside and multiplying it by each of the 3 terms on the inside. Okay, so let's keep on keeping on. I want to get down through worksheet 2 before I'm done with stuff today. One of the nice things about this being a video that I'm sending you is if this is a bit too much to digest all at once, you can simply just pause and come back to the video later, of course, right? You don't necessarily need to power through the whole, like, boy, it's gonna be close on an hour by the time I'm done. But you know, hey, gotta be thorough, right? That's the point. So I'm going to carry on here now. Math 1101A, Unit 3, Worksheet 2. State the greatest common factor for each, and then factor. Okay. So now it starts getting a little bit different, but you'll see that the actual basis of what we're doing is still the same as it ever was for these worksheets. Okay, so I'm going to start off with A, and then I'm going to do some of the more complex ones. So let me zoom in a little, and then move on back over. So I have 6y minus 12. So that's a pretty straightforward one because there's not a whole lot of different numbers there. But it's a good example to show the basics for what we're doing here. So when we're finding the greatest common factor, what that means is we need to find the factors of each term, right? So I'll write this down over here. To find Oh, I guess I should. Oh, yeah, yeah. Never mind, never mind, never mind all that. Okay. Just look behind the curtain there. Just tear down the whole thing. Anyway. So to find the greatest common factor of a polynomial expression, we must find the prime factors of each term. Okay? So what does that mean, the prime factors of each term? Well, strangely enough, in this instance, it's the coefficient, not the variables, that give us the most trouble. Because the prime factors of a variable is just the variable. And you'll see what I mean when we get to a question like G here now in a second. But for A, suffice it to say, what I'm doing is we're just had to find the prime factors of 6 and 12. Now, you might know off the top of your head that 6 is a factor of 12, but I'm going to work through this from the very basics so you see how the operation goes. So I'm going to break 6 down into its prime factors. That's going to be 2 times 3. Done. 12 is going to break down into its prime factors. That's going to be 2 times 6, and 6 is 2 times 3, like so. Right? So then our GCF, you'll recall, is always the numbers that are in common in each. So in common in each, there's 1, 2, and 1, 3. So the GCF is 6. Okay? That's just a quick recap of the way it looked back on this example over here, back on worksheet 1. Right? Just a quick, another one like that. So, but what this tells us now is we can divide both these terms by 6. We can also check and see if there are any variables in common, because we can also divide by the letters, right, or the variables. Here there's a y in the first term. There's no y in this term, so we can't divide by y, right? Because in order to divide by y, there would need to be 1 in each of the terms. Here there's only a y in one of the terms, so we can't divide by it. But we can divide by 6. So now we divide each term by the GCF. Now, how do we write this? The way we write it is we do a 6 and then we open a bracket, right? And then inside the bracket, we write each of the terms divided by 6. So what's 6y divided by 6? Actually, I'll write this out. I'll write this out. 6y divided by 6 minus 12 divided by 6. This is not a step that we would always write down. I'm just showing you this step just to be thorough, to show you the way it would work. Right? But actually what we would write is 6 outside of y minus 2. Why is it 6 outside of y minus 2? Well, y is 6y divided by 6. 2 is 12 divided by 6, and it's a minus because this was a minus. It's actually a minus because this is a negative 12, and negative 12 divided by 6 is negative 2. 6 of one, half dozen of the other, really. So now let's go on and do G. And G is a touch more involved, but as you'll see here now, G is identically the same in effect, right? So it's going to be 36 x cubed y to the 5 minus 24. Is that x to the 8? My word. 24x to the 8 y 5. Now we live in a universe of 3 spatial dimensions, so we don't have fancy names for exponents of 4 and up. Perhaps in other parallel universes with more dimensions they would, but you know, I've never visited a parallel universe. It's like on Fringe, right, or something like that. That was a pretty good show. Actually, one of the main characters in that was named Peter, right? Yeah, but he was the least likable of all the characters. Easily the least likable character in Fringe is Peter. He's just so annoying and boring and normy. Like, come on. Olivia's much better, especially faux Olivia. But the best is, oh, what was his name? The doctor? That old like brilliant chemist guy who travels through alternate universes and makes a lot of acid. Anyway. I don't know. This is getting back into the old stuff, like in the oh, look, it's Peter being a distractible idiot again. Yes, indeed. So I'm just going to break down each of these initial terms here, right? And just like I was doing before, we broke down 6 and we broke down 12. So here now we're going to be breaking down 36, 24, and 54, right? So 36, I'm getting a bit tired of always breaking down 36. We've done this one a bunch of times now. 2 times 3 times 2 times 3. Just going to keep doing that. So that's going to equal 36 equals 2 squared times 3 squared. 24. You might know off the top of your head that one is 3 times 8. But I'm going to break that one. I'm going to divide by 2 as long as it's even. Like I said, because I find that to be a good methodical way of approaching it. And I frequently do find that students appreciate having a methodical way of going about this, even if the methodical way would not always be the quickest. Frequently, students find it quite useful to have a way that is sort of regimented and will always work, right? So if you see an even number, you can divide it by 2, and you can keep doing that until you don't see an even number anymore. Sometimes you'll have a faster route from the start if you recognize it. Like 54, I know that's 9 times 6 because that's in our times tables, right? So I could immediately bracket it off into 9 times 4, but I'm going to do always the dividing by 2, like I said, so it's going to be 2 times 27. But now, since 27 is an odd number, I had to go to the times table and recognize that 27 is 3 times 9, which is 3 times 3. You also could have recognized that 27 was 3 to the power of 3, but either way. Like I say, right, 6 of one, half dozen of the other. It doesn't really matter what way you get there as long as you get there. So here we have our 3 coefficients broken down into prime factors. Now we can find the GCF. Again, the GCF is going to be the number that is in common. Right, so we have 2 2's here, 3 2's here, and 1 here. So there's 1 2 in common amongst all 3. 2 3's here, 1 3 here, and 3 3's here. So we have 1 3 in common amongst all of them. So our GCF is 6. So we know that we can divide each of these by 6. Now, we can also, we can also find a common factor amongst the variables as well. Okay, so I showed it to you without the variables first, just so we could do this, but the variables are not any different really, right? Because in the first one we have, I could even write them out the same. So in this one we have x cubed y to the 5. And you notice that that's sort of, it looks kind of the same as this, right? So what I could have said is 2 squared times 3 squared times x cubed times y5 for this first one, right? So I could have said, 36x cubed y5 equals 2 squared times 3 squared times x cubed times y5, like that. I could have said all this. I'm not going to bother with writing this first part out again here. I'm going to do it separately. But this is just to show you that there isn't any sort of big difference between if it's a number or if it's a variable. The fundamentals behind the way the math works is exactly the same. But I am going to do them separately here just to show you. So then this term has x cubed y to the 5 in it. So I'll just cross this part out here now because I'm not concerned with that for the moment. This one has x to the 8 y to the 5. This one has x cubed y to the 6. So again, we need the greatest common factor. So the GCF here, there's going to be x cubed, right? Because there's 3 x's here, 8 x's here, and 3 x's here. So there's 3 x's in common. There's 5 y's here, 5 y's here, and 6 y's here. Oh, I gotta move my head. 6 y's here. So we have y to the 5 as common. So the thing we're going to be dividing by is actually 6x cubed y to the 5. Right? Because we take this, we're going to take this and bring it down here. We're going to take this and put it over here. And it's going to become that. Okay, you don't need to write out your work exactly the way I'm writing it out, but this is just, I'm trying to show you very piece by piece the way that this goes together. So now we're going to go on and we're going to do the same sort of deal we did over here. Notice over here what I did is I opened up a bracket, right? I put the GCF outside, and then inside I did each term divided by the GCF. So I'm going to do that same thing here. My GCF is 6x cubed y to the 5. And that's going to go outside a bracket. And now again, this step isn't one that you necessarily need to write down, but I'm going to write it down here now to show you clearly how this is working. So 36x cubed y5 divided by 6x cubed y5 minus, because our operation in between is going to stay the same. And keep it all on screen at once here. 24x to the 8 y to the 5 over 6x cubed y to the 5 plus, because the operation stays the same, 54x cubed y to the 6 over 6x cubed y to the 5. Okay, it's rather long. Well, what am I going to write down in here? Well, I'm going to start dividing here now. We know that 36 divided by 6 is equal to 6. X cubed divided by x cubed, will those go away? Right? Because there's the same number of x's on top and as on bottom, those go away. Y to the 5 divided by y to the 5, those cancel as well. All we're left with is the number 6. Right? So I'm going to keep it spaced roughly the same way apart so you can see how they go down one to the next. 24 divided by 6 is 4. X to the 8 divided by x to the 3, where we're going to be left with 5 x's on top, will be left here. Y to the 5 divided by y to the 5 is 1, because any number divided by itself is 1, so those go away. So then the next step, 54 divided by 6 is going to be 9. X cubed divided by x cubed, again, is 1. Y to the 6 divided by y to the 5 is going to be just a y. So now to write it again without all that awkward looking space left between it, that's going to be 6x cubed y to the 5 outside of 6 minus 4x to the 5 plus 9y. Now that's quite a... Again, right, it might look a little intimidating at first because there's so many different numbers and variables and stuff all being thrown around in here, but at no step here did we use anything other than the math that you've been looking at so far. Right? It's gotten a little bit more complex in the sort of how many different terms there are and how many different variables and coefficients are in those terms, but it hasn't, the actual math that we're doing is still the same as it ever was for this unit. Now I will do one of question 3, because question 3 is very similar to question 2, and then I think hopefully you'll be equipped to handle the rest of these ones. So finally, Math 1101A, Unit 3, Worksheet 2. Oh, let me go back over so you can see what I'm going to be writing down. Yeah, so we're going to simplify each expression by combining like terms. Okay. Not terribly difficult, honestly. None of these are... let's do C. Let's do C. It's probably the most complicated of them. So that's negative 7n to the 3 minus 5n squared plus 2n minus n squared minus n to the 3 minus 12n. Boy, oh boy. Okay. Well, what does it mean to combine like terms? Well, combine like terms means we're going to all the numbers that are just numbers, don't have any variables. Those are going to combine, and we're going to combine all the variables that are the same. The thing is, even though all of these have an n in them, they're not all the same because different powers of n we treat as different variables or different. They're not different variables. They're not like terms. Rather, the only way for them to be like terms is to have the same exponents as well as the same variables. So what I'm going to do is rewrite these to group the terms together by if they have like terms or not. So the n cubes are similar. So there's negative 7 n cubed here and negative n cubed here. So I'll write those down. Now I'll do the squared ones. So minus 5n squared from here. And then this one here also has a negative n squared. So it's going to be a minus n squared there. And then we have our linear ones. So we have a plus 2n minus 12n. So all I've done in this step is just rearrange them. Now I'm just going to add or subtract based on what the operation between the terms is. So here I have a negative 7n cubed minus another n cubed. So this is just negative 7 minus 1, right? If you owe someone $7, then you owe them another $1. We know you owe them 8 in total, right? So this is going to be a minus 8n cubed. Negative 5n squared minus another n squared is going to be a negative 6n squared for the same reason. And here there's a plus 2n and a minus 12n. So 2 subtract 12 is negative 10. Right? And now we're back to a question just like in part 2. So once we get to this point, which is having combined all our like terms together, now we just go back and do what we did in question 2. So first we're going to get our factors, right, of 8, 6, and 10. Now, I'll go through and do it the long way. You might be able to look at that and say, well, the biggest thing that can divide in each of those is 2, right? But I'm going to go and do it the full-on way, like I've been doing. We know the GCF is 2, right? Because 8 is 2 times 2 times 2, or 2 to the power of 3. 6 is 2 times 3. 5 is 2 times 5. So the only thing that's in common between each of them is 1, 2. So we know our GCF is 2. We also know that there's an n in each. There's n cubed here, n squared here, and an n here. So since there's at least one n in each of them, I'll say the GCF is 2n. We could also make it a negative 2n. We could, because there is a negative here, a negative here, and a negative here. The thing is, you can always divide by a negative, and it just flips the signs. So for now, I'm not going to be concerned about a negative inside or factoring a negative out. I'm going to call this 2n outside, right? So then on the inside, I'm going to divide each of these terms by 2n. So negative 8 divided by 2 is going to be a negative 4. N cubed divided by an n is going to be an n squared. Then negative 6 divided by a 2 is going to be a negative 3. N squared divided by an n is just going to be n. And then negative 10 divided by 2 is going to be negative 5. N divided by n is 1. And of course, in multiplication, we don't need to write down times 1 because it doesn't do anything. And there we go. So that is the answer here. So a small bit simpler than question 2. Question 2 is really the sort of the meat of this worksheet. All right. So that is, that's quite a bit of video there for you to go through. But hopefully that is painstaking detail. Hopefully it's not, hopefully you've made it to this point, still paying attention and not falling asleep. So good on you for that. If you have fallen asleep, Lauren, please wake up. This is the middle of the day. You need to be doing some math work. Anyway, Yeah, it's a constant battle, right? It's a constant battle to stay awake while Peter's here droning on about math. But look, you can pause the video, you can go back, you can rewatch little bits of it. So hopefully this will be a good way for you to see exactly how each of these questions work.